Hello everyone, I am Aniruddha and I am a PhD scholar at IIT Indore. I will be your TA for this course, Missile Theory. And in this week one, what we have discussed is we have discussed extended real numbers, we have discussed semi-algebra, algebra, and sigma-algebra. Okay. So, if you people have looked at the assignment problems, there are some problems based on monotone classes, but those lectures are not included in week one. So let me give you the definition of monotone class first, and then we can go to our. Okay. So let me write the definition. So let X be a non-empty set. Let me change the color. Yeah. So let X be a non-empty set, and say M is a collection of subsets of X. So it is a subset of common set of X. We say that M is a monotone class. M is a monotone class if the following things happen. First one is that for every sequence an in M, such that for each n, this an is contained in an plus 1, we have their union is again contained in n. And the second thing is that for every sequence an in M, such that for each n, an contains an plus 1, we have their intersection is in M. Okay. So, just a few remarks. These sequences which satisfy this property, they are called, they look like monotone increasing sequences, right? So, I will just call them monotone increasing. Sequence of sets. So I'm calling them. This is the name I am giving it. This is a monotone decreasing sequence. Okay. So the first question is whether we have any monotone classes with us or not. So what do you think? Are there any monotone classes? Can we think of some examples? So it will be better if this session is interactive. So I've allowed everyone to open their mics. You can speak. Just if somebody is speaking, don't open your mic at that. Okay. So yeah, can someone tell me? Do we have? Can you think of any examples of this monotone classes?
So a set of intervals in a certain way.
Set of intervals. Do you mean the collection of all intervals?
Yes, sir.
So let us see. Uh, so you are Jitesh, right?
Yes, sir.
So Jitesh told us that let us look at. Let us take this M as the collection of all intervals in R. So Jitesh, why do you think that this is a monotone class?
Sir, because I can always choose a monotone sequence, and then I know that unions of intervals is again an interval or intersection.
Is that so? See, this is an interval, right? 1, 2 is an interval. 3, 4 is an interval, but their union is not an interval.
Yes, sir, but one some interval must be contained in the other.
Correct. So what you are essentially using is, so I guess this is easily provable, right? So we are using this fact that if INs are intervals, such that their, sorry, we have proved their union is such that IN is contained in IN plus 1. or in is contained in in contains in plus 1, then union in, this is an interval, or equivalently intersection in is an interval. But how will you prove this? Can anybody else give some idea? For that, actually, we require the definition of an interval, right? Does everyone know how do we define an interval? Can somebody say whether they know or not?
Yes, sir, we already know that.
Yeah, so can you tell me the definition of an interval?
Sir, interval in real line?
Yes, yes, on the real line.
Sir, any subsets of R with
Yes.
any subsets of R, you can, which is continuous, sorry, which is not break anywhere.
Oh, but that is not the definition, right? Okay, so let me give the definition as well.
Sorry, sir, if any two real numbers, then all the real numbers between that two real
Between
number
them.
must be in the interval.
Correct. So a set I in R, this is an interval. If you take any two real numbers A and B in I, and let C be in R be such that A is less than C is less than B, so C lies between A and B, then we must have that C also belongs to I. So is this definition clear of an interval?
Yes, sir.
Okay. So with this, we really want to prove that whenever we have a sequence of intervals, which is one is contained inside the next, then their union is an interval. So that means if I take any 2 points in union IN, I need to prove that all points in between are inside the union IN, right? So let us see. So let A and B, let them be in the union of IN. So, okay, I will just mention it here. This notation I will use interchangeably with union n equal to 1 to infinity. So, if you have any confusion at any point, please tell me. It is really a habit of writing this way. So, okay. Then what does it mean? Then A belongs to I m naught and B belongs to I m naught for some n naught and m naught in n. Okay. Now what? Can we say that A and B are contained in the same interval? In some same interval? Yes. See, we know that IN naught is contained in IN naught plus 1, and then it is contained in IN naught plus 2, and so on. So I can definitely say that AB, they belong to I maximum of N naught N naught. Correct? Does everyone agree with this?
Yes, sir.
Yes, sir.
So now once they are in one particular interval, that means for every C in R with A less than C less than B, C must be inside this I maximum of N naught M naught, because this is an interval and this is anyway contained in the union of all INs. So C is contained in the union of all IN, and therefore this union, this is an interval. Or equivalently, what we want to write is union of IN belongs to this N. Similarly, one can prove intersections. I'll leave it to you to check whether this intersection of intervals is again an interval, and then you will conclude that whether M is really a monotone class or not. Okay, so this was one of the examples. Can we have some simpler examples of monotone classes? Something very trivial, which we can directly see that okay, this is a monotone class. Yes, anyone? Or maybe you can try.
Sir,
Okay.
subsets, finite subsets of real number.
Finite subsets of real numbers. Uh, so do you mean to say that let us collect all the subsets of R such that E is finite?
Yes, sir.
Okay. So let us see this. Okay. Does everyone think that this is a monotone class? Yeah, maybe we have to work a bit, right? Okay. Let us take a sequence. Let us see what. Let us try to prove that this is a monotone class. If we get stuck in between, then we'll know how to find a counterexample to this. So let us take a sequence En in this N. So we cannot really write this in a subset. En be a sequence in N. Then we want to know whether union of En is finite or not. So can this happen? It also has this property that En is contained in En plus 1. So yeah, this may not happen in general, right? Why?
Yes, sir.
Because
Yes,
if
sir. It can be
yeah,
infinite.
can you give a counterexample then? Yeah, Prasandeep, can you give a counterexample?
Yes, sir. So the countable union obviously will be infinite, obviously.
Well, not necessarily infinite, but it may not be finite as well, right? For example, if
Yes,
En,
sir.
yeah, is it not? Yeah, now it will be. If En is singleton X for every n, this is a sequence, right? And it satisfies the fact that En is contained in En plus 1 because all sets are same. Then the union is singleton X and it is finite. But what if we take this? En is this set 1 to n. The union of En is all of natural numbers. This is not. So I guess everyone can convince yourself that En is contained in En plus 1. Not very difficult to see. Okay. So, all right, these were some examples of monotone classes. What I was really expecting was, let us look at this set, empty set and X. Is this a monotone class? Yes.
Yes, sir.
Why? Uh, can you tell me why is this a monotone class?
Yes, sir. So for the sequence, we can choose the same set again and again. So it will be contained in itself.
Correct.
And then,
So basically, the only sequences possible here are eventually constant sequences, right? So the union is basically a finite union, and the only two unions possible are either you take union of empty set with X, or X with X, and all of these unions are in them. So fine. This is a monotone class trivially. So this was about monotone classes. In fact, let me give you a question. you can try this. This is also easy. Let n as a subset of Px be finite. That means M has only finitely many subsets of. Then is M a monotone class? So perhaps you can think about this and we'll discuss either towards the end of this session or next week. Okay, so you please remember the definition of a monotone class. All we require is that increasing sequence of sets, their union should be inside M. For a decreasing sequence of sets, their intersection should be inside M. So, okay, are there questions till now? Okay, so no questions. So let us go to the discussion of whatever happened in week one. Do you want to ask anything from the lectures or any other thing? Right? So Shashikant, you actually mailed me, right? Do you want to ask something? I think he's not here. So anyone else? Any question from the week's contents? Of his writing. It's a set of all possible intervals. Nature of interval. I really could not understand the question. So if you could unmute it, then perhaps explain what you want to ask. Yes.
Hello, sir.
Yes. Tell me.
Sir, we were in the first class earlier discussing about a set of all possible intervals is a semi,
Semi-algebra.
but not an algebra. But then intervals means what kind of intervals? For example, if I take some set of all possible intervals in real number set, then if I
Uh-huh.
take some open set, its complement would not be definitely not an open set because like it will be half open, half closed.
Yes,
So
complements of open sets are need not be open. That's right.
I'm saying in that question, the class it was question was set of all possible intervals in R.
Uh-huh. Yes,
It is a semi group,
it is a semi-algebra.
semi algebra. But then the complement, if I take some interval, I mean interval means what kind of interval? Is it a
Any,
divided by
any interval.
any
It may be
interval?
open, it may be closed, it may be half open, half closed, any kind of thing.
Okay, thank you.
So actually, I just discussed the definition of interval here. To just look at this. What is an interval? A set is an interval if you take any 2 points in that set, all the points in between those 2 points are again in the set. So this does not tell us anything about whether I is open, closed, or anything, right? So when I say an interval, it could be of any type. Okay. Any other questions from the previous class?
Interval has to be continuous, but open set need not be continuous, right?
Yeah, but there is nothing called as continuity of sets.
Okay.
Yeah, so a set is an interval. Yeah, what you mean to say is it should be connected, right? Interval is necessarily connected.
Yes, yes.
Yes, yes, that is true. In fact, actually, you are not equipped with topology, but there is a result that says that uh, the only connected subsets of R are intervals. So, okay, anything else? Okay, maybe not. So let me give some exercises. We can solve it together. So see, we have already seen that this C, if I collect all intervals, this is a semi-algebra. What if I correct this set? C1 is set of all open intervals. Is this a semi-algebra? Yeah. Somebody unmute and please share your thoughts. So, okay, let us go one by one. Is empty set an open interval of R?
Yes, sir.
Okay. Is all of R an open interval of R?
Yes, sir. Obviously, it is the entire real line is open and closed.
Correct. So, yes, let me just write here R and empty set, they are both open and closed. And in fact, they are intervals. Okay. What about intersection of open intervals? Are they open intervals?
Yes.
Yes. Why is that so? See, we have already seen that intersection of intervals is an interval. Why should it be open?
Sir, since they are open sets and we are taking a finite intersection.
Correct. So the next thing that we really want to use is that finite intersection of open sets is open. Finite intersections of open sets is open. Okay. What about the complement? Can the complement of an open interval be written as a union of open intervals? So it all this boils down to this question, right? And the complement of an open interval be written as a union of open intervals. So what do you think?
Sir, maybe not because the complement would be a closed set. And
Yes,
then if you want a disjoint union of open intervals to be equal to a closed set, there you can always find a counter example so
correct.
that the
So
statement is not.
yeah, just provide me the counterexample then.
Um, uh, we can take the closed. Uh, so we can take the open interval 0 comma 1.
Yes. Look at
So
the complement. The complement is
the complement is minus infinity to 0 closed
yes,
union 1 closed to infinity.
correct. So this is not a union of open intervals. And if we really want to go into the rigorous proof of this, that this cannot be written as the union of open intervals, we simply have to use the fact that if at all this, suppose that this is a union of open intervals, then the set has to be open, right? But then the only open and closed set is either R or empty. But this is neither R or nor empty, right? Okay, so is this clear? So this is not
Yes,
a
sir.
semi-algebra. So what we conclude, C1 is not a semi-algebra. Okay, similarly, let me again give you some questions to think, and that we will look at either towards the end of this discussion or next time. So the question are: look at these sets. C2, correct all closed intervals, and C3, let us select all half open, half closed intervals. So here in C3, you are free to choose the open whether left or right, half closed whether left or right. So you are free to choose that. So it has both these type of elements, AB and AB. They're not open. Whether these two are semi-algebra. Yeah, I guess you can directly see that C2 is not a semi-algebra because whatever we discussed, we just have to directly apply it here. But C3 might require some explanation. So we'll come to this later. Okay. Uh, Next, let us look at one more. Suppose that X and Y, they are non-empty, and this F and G, they are semi-algebras of X and Y respectively. Now the question is whether their Cartesian product is a semi-algebra. Is F cross G a semi-algebra? Oh, X cross Y. Okay, so what do people think? Is this going to be a semi-algebra? Okay, so let us again go step by step. Let us first see whether the empty set is in F cross G. Is it there?
Yes, sir.
Okay, why?
Sir, because F and G both are semi-algebras, they both contain the empty set.
Right.
And
So
so,
empty set, Cartesian product empty set is empty, and then empty set is inside F cross G. Okay. So we have this. What about X cross Y? Is X cross Y in F cross G?
yes, sir.
Because of the same reasoning, right? That X is in F, Y is in G, so X cross Y is in F cross G.
Yes, sir.
Y is in G, so G implies X cross Y is in F cross G. Okay. What about the intersection? So if A and B they are in F cross G, does A intersection B also belong to F cross G? Yes. Anyone? Okay. What is the meaning of A and B being inside F cross G? Do we have some representation of A and B?
Sir, A could be a Cartesian product of subsets of F and X and Y.
Correct. So A can be written like A1 cross A2 and B can be written as B1 cross B2, where A1 and B1 are in F and A2 and B2 are in G. Okay. So let us look at A intersection B. A intersection B is A1 cross A2 intersection with B1 cross B2. So now, can I write it like this? So I'm asking this, whether this is equal to A1 intersection A2 cross B1 intersection B2. Is this true? Yeah. Sukhvinder, are you here? Can you try?
No, yes, sir. I'm here.
So, can you tell me whether this intersection can be sort of
Interchangeable.
distributed over the partial product? Can you do this?
Sorry, sir. I can't. I'm
Okay.
trying to write it down, but
Okay. So see, let us try to write down the two definitions. Then A1 cross A2 intersection B1 cross B2. By definition, this is collection of all xy in x cross y such that xy is in A1 cross A2 and xy is in B1 cross B2. Do you agree with this?
yes, sir.
Let us now split these two definitions as well. So this is all those xy in x cross y such that x is in A1, y is in A2, x is in B1, y is in B2. Yeah?
Yes, sir.
Okay. So what is this? This is xy in x cross y such that x is in A1 intersection A2 and y is in B1 intersection B2. Oh, sorry. Yeah,
Yeah.
not quite. A1 intersection B1
Even
and A2 intersection B2.
why A2 into B2.
Yeah.
Yes,
Yes,
this is visible now.
is this fine?
Yes, sir.
But then this is what is this? This is A1 intersection B1 cross A2 intersection B2. Right?
Yes. Yes.
So we can do this. This is correct.
Mm.
No problem in that. Okay, now what? Can we say that this is in F cross G? So notice that A1 and A2. Oh, yeah, see again here I have written this. Yeah, sorry for the mistake. This is A1 intersection B1 cross A2
A2
intersection B.
intersection B2.
So notice that A1 B1 are in F, so their intersection is in F.
Mm.
A2 B2 are in G, so their intersection is in G.
G.
And therefore, all this their cross product, their Cartesian product is in F cross G.
F cross G. Thank you.
So the intersection property is fine. What about the complement? So this might require some work. So let me start. Suppose that A cross B is in F cross G. Okay. First, can someone tell me what is A cross B whole complement? Maybe you just tell me the definition. Okay? Yeah. Connect all xy and x cross y such that what happens? Yeah, Shashika, can you try?
X cross Y minus A cross B.
Yes, that is fine. But what type of points are there? I want to know. So you collect all xy and x cross y such that something
Actually, A
happens.
is X coordinate X axis and B as Y axis. It will become a rectangle. So X cross Y minus A cross B is something like bigger rectangle minus smaller rectangle. Again, that we can split as rectangles.
Yeah, I want to know how will you split that. But it is in diagram. It is visible, right? If I make this rectangle, then the what we say the complement is going to be this, right? But I want to write it as something, and you want to split it like this. Okay?
That is nothing
So
but
this is R1,
disjoint
R2, R3.
union, disjoint union of subsets of x cross y. That
But
is
are they in F cross G? They are degenerate of subsets of X cross Y. That is fine. See, okay, we will go to that. Let us not jump. Let us try to first write A cross B complement. What is that set by definition? So by definition, it is collection of all X, Y, which are not in A cross B, right? If X comma Y is not in A cross B, it means either X is not in A or Y is not in B. Correct?
Yes, sir.
Okay. So this is basically looks like a union. So you tell me whether whatever I am writing is correct or not. Can I write this as A complement cross Y union with A cross B complement? Yes.
Sir, sorry.
Yes, yes, tell me. I have somebody unmuted, so tell me what do you want to say?
Sir, in this way, X will be in both A complement and A.
No, no. I am writing union, not the intersection.
Okay.
So see, either X is not in A. If X is not in A, then you can take any Y, right? That will satisfy the given condition. So one of the part is A complement cross Y. Second is if X is in A, then the only possibility is that Y cannot be in B. So the second part is A cross B complement.
Yes.
So I hope that everyone is convinced. If someone has any doubt, please tell me.
sir, x cross b complement would come, I think.
Yes, X cross B complement is also correct. But I just want to write it as a disjoint union, right? Ultimately, I want a disjoint union. So we have to really
Okay.
shorten that thing. See, even here in rectangle, we just draw this everything again. So this is a rectangle A cross B. This is our A. This is our B. So what is its complement? I want to split it this way. Okay? So either something is in A complement, in which case it can really, sorry, take any value in Y. So the
A,
first
A
set is
cross y means
this.
that A strip, the entire vertical A strip will not come.
Yes, in this entire vertical A strip will not come. The left hand side of A strip is there, the right hand side of A strip is there. So this is A complement intersection Y. The second set which I want to take is this vertical strip in which A comes. So this is A cross B complement, right? And their union is the complement of A cross B.
Understood now, sir.
Okay. Now notice that A is in F, so I can write it as union of AIs, I from 1 to N, union with A cross union J from 1 to N, BIs, right? Where AI is in F, BJs are in D, and the unions are disjoint. Okay. But now it is easy to see that this is just union I from 1 to N, AI cross Y, union with union J from 1 to N, A cross BJ. And all this is a disjoint thing. So use red. So is everybody convinced with this? All the arguments that I have provided? Yeah, please, someone respond.
Yes, sir.
What about Sukhvinder?
Yes, sir, I'm convinced. Now it is look like semi-algebra.
Right, right. So it is a semi-algebra, right? Like, we have proved that it is a semi-algebra. And what about Haha Masi? Is it fine with you? Perhaps he is not here. Okay. Anyway, so what does this say? This is indeed a semi-algebra. Okay. Uh, what is the next natural question that you should ask? Yes, Prasanjit, do you want to ask something? No. Okay. So, what is the next natural question that we should ask by looking at this example?
Is it algebra or not?
Yes, whether it is algebra or not. Or a better question is, given two algebras, whether their Cartesian product is an algebra or not, right?
Hmm. Hmm.
So, let us see this. Given algebras F subsets of X, G subsets of Y, is F cross G an algebra? Yeah. So, what do you think? Is this going to be an algebra? Actually, we have seen this. But it really requires. Okay, let us look at this. Let us look at the diagram I made above. See, right. So this rectangle, actually, if I take the complement, it is not going to give us another rectangle, right? Complement of rectangle is not a rectangle. And is the set of all rectangles an algebra? Have we seen that?
No, I think no, because
That
you
is
can't just a
an
single
algebra.
rectangle.
Yeah, it is a semi-algebra, but not an algebra, right?
Yes.
So even if the complement is inside F and G, because of this union here, there is going to be a problem, right? For algebra. So okay, let me just you know perhaps you can try this. Okay, try to prove or disprove. So I have given the hint that maybe that this union is going to cause a problem, if at all it causes some problem. And this we will definitely discuss next time. It is really interesting to try. Okay. So next, what I want to do is, so, okay, let me start writing. Then I will explain. Suppose that x and y are non-empty sets, and I have a function from x to y. So this is just a function. Okay, I am not saying that x and y are topological spaces or any other structure on x and y. So I cannot say anything about continuity or any other. This is just a function. What I have is, suppose I start with a semi-algebra in y. be a semi-algebra. So then let us define F inverse C as you collect all the pre-images of the sets of C. So this is a collection in X, right? Collection of subsets of X. So the question is whether this is a semi-algebra. Is F inverse C a semi-algebra? So essentially what I am doing is I want to sort of pull back C uh, through my function. Okay, so what do you think? Is this F inverse C going to be a semi-algebra? Yes, quickly. Can someone just or let us go step by step. Is empty set inside this collection? Yeah, Sukhvinder, is empty set inside this collection?
Maybe say yes.
Why?
So because C is an semi-algebra.
Yes.
So
So empty set is in C, that we know. Then what will happen? Let us look at F inverse empty set. This by definition is in F inverse C, right?
yes.
Okay. But what is F inverse empty set?
Oh,
Sashikant, what is F inverse of empty set?
No idea, sir. I was thinking what is the nature of function f,
Oh,
because if
see,
v
this
is
inverse is not
root
the
of
inverse of a bijection. Okay, it is the pre-image. Okay. Then perhaps I should write all this down. So, where should I write it? Maybe I'll write it here. So, given a map F from X to Y, and say A is a subset of X, B is a subset of Y. When I write F of A, it means you collect all images of X as X varies in A. And when I say F inverse of B, it means you collect all those elements of X such that their image is in B. So this is called the pre-image. And this is called the image of A. So here F inverse of empty set means you collect all those X such that their image is inside the empty set. Can such a X exist?
no, sir.
No, right? Because nothing can be inside empty set. So this is empty. So empty set is in C, therefore empty set is in F inverse C. What about X? Does X belong to C? Yes, Sukhwinder, are you saying something?
But I'm figuring this out.
Okay, what can you say about this set? F inverse of Y. By definition, it is collect all those X whose images are in Y.
Hmm.
Oh, sorry. Whose images are in Y. What is this set?
whole x.
All of x, right? Because f is a function from x to y. So any point in x has image inside y. So this is all of
Hmm.
x. So empty set is in C. Sorry, I'm not written it correctly. Empty set is in F inverse C. X is in F inverse C. Okay, what about the intersections of two sets? So suppose that A and B are in F inverse C. Does this imply that F inverse of A intersection F inverse of B? This is again in F inverse C. So see, okay, what is the natural thing that you expect? Jitesh, can you just answer this? What is naturally coming to your mind by looking at this expression?
Yes, sir. I'm still trying to understand.
Oh, is that first 2 points clear that empty set is in F inverse C and X is in F inverse C?
Yes, sir.
Okay. So see, now the question is, you take any two sets in F inverse C. Oh, yeah, sorry. See, I'm not really written it correctly, right? I jumped a few steps. So the question is the intersection B, whether it is inside F inverse C. So first, okay, Jitesh, you tell me, what does it mean that A and B are in F inverse C?
So it is the set of all elements in X such that f of x is in A and f of x is in B.
Correct. So A is the pre-image of some set. Let us call it as E. And B is also the pre-image of some set. Let us call it as F. Right?
Yes, sir.
Oh. Now A intersection B, this is what? This is F inverse E intersection F inverse F. Okay. So if you look at this expression, what thing comes to your mind naturally? What do you expect? Okay, do you expect that? Yes, tell me. Tell me, tell me.
Yes, sir. I'm trying to think.
Okay, so tell me whether you expect this or not. Do you expect that this is equal to F inverse of A intersection B?
Yes, sir. Yeah.
Okay, so this is what we expect, right?
Yes, sir.
Let us see whether our expectations are met. Again, we have to write here. Let us look at F inverse A intersection F inverse B. So by definition, this is the collection of all those points such that X is in F inverse A and X is in F inverse B. Now let us again use the definition of F inverse A and all. So this is all those X such that Fx is in A and Fx is in B. Correct?
Yes, sir.
Oh. But this is just all those X such that Fx is in A intersection B. But if Fx is in A intersection B, that means X is in F inverse of intersection B. So this is F inverse of, right?
Yes, sir.
So this is true. Now once we have this, I guess now we are through, right? Because A intersection B will now be in C, implies that F inverse of A intersection B is in F inverse of C. But this was, oh, sorry, E and F. Yes. But this is F inverse E intersection F inverse F, which was A intersection. So intersection of two sets of these pre-images are again a pre-image. At least C is closed under finite intersection. What can you say about complement? So again, let us take A in this F inverse C, which means that A can be written as F inverse of E for some E. And then I want to look at A complement. Okay. So what is A complement? A complement is F inverse E whole complement. Again, by looking at this expression, what do we expect?
F inverse of E complement.
Correct. We expect that this should be equal to F inverse of E complement. Now, whether this is true, let us see again. So again, F inverse of E whole complement, this by definition is collect all those X such that X is not in F inverse E. But if something is not in F inverse E, it means its image is not in E. Correct? Does everyone agree to this?
Yes, sir.
Okay. So this is what? If Fx is not in E, it means so this is yeah. Oh, sorry. Yeah, I have to write one more step. So X in X, such that if Fx is not in E, it must be the complement, right? But this is the definition of F inverse of E. So this is again correct. So therefore, A complement. This is F inverse of E complement. Now E complement can be written as a disjoint union of some Fj's, J from 1 to n, okay, where this Fj they belong to. Now what? What do we expect from here?
Disjoint union of F inverse of the
Correct.
six.
So disjoint union of F inverse of X. Okay. Now there are two questions, right? So this gives rise to two questions. One is that is F inverse A union B equal to F inverse A union F inverse B? And the second question is that if A and B are disjoint, if A intersection B is empty, then is FA intersection FB also? So okay, so I will not really write the solutions to this. I want you to try it. Suppose you want to prove one, how will you prove it? So let us go in a cyclic way. Let us start with Jitesh. Jitesh, how will you prove one?
Yes, sir.
You tell me, what will you do?
So initially, we just show that each one of the two sets are subsets of each other. So that is how.
Correct. That is how you prove equality, right? Okay.
Yeah.
But before that, let us write the definition, right?
Yes, sir.
Okay. So you tell me, what is the definition of F inverse A union B?
So this is equal to all x in capital X, such that
Yes.
f of x belongs to a union. Yeah.
Correct. But what does this mean? If F of X belongs to A union B means what?
That f of x either belongs to a or b.
Or yes, F of X belongs to B. Okay. But what does this mean?
That either x belongs to f inverse of a, or x belongs to f inverse of b.
Okay. So you are sure that all these are equalities, right? Nowhere substitute.
Yes, sir.
But what does this mean?
That X belongs to the union of the inverses.
Correct. So this is F inverse A union F inverse B, right?
Yes, sir.
So this one is one has answer yes. Okay. What about two? So perhaps Sukhinder, can we try?
Yes.
Yes. So the question is, if A intersection B is empty, then whether FA intersection FB is also empty.
Yes,
Ah,
sir.
I mean, yeah, not FA intersection FB, F inverse A intersection F inverse. Okay. Yeah. So why is it true?
So first, we should write definition
Okay, let us write definition. F intersection FB, right?
is equal to
What is this?
all the collection of x such that
Yes.
uh, fx belongs to A and fx belongs to and B also.
Okay, so you have skipped one step, right? You collect all
Yes.
those x such that x is inside F inverse A and x is inside F inverse B. But then
Yes.
that would mean that fx is inside A and fx is inside B. Okay. Then what?
But there is no
Yeah. So this is empty.
such functions.
Yeah, this is not empty. I mean, uh, what happened? Yes. This here. Yeah. So because A intersection B is empty, this cannot happen, right? So this is empty.
Yes, sir.
Okay. Uh, Sashikant, can you give me another proof of this?
I'm thinking if it is wrong by contradiction, suppose f inverse A intersection f inverse B equal to some set x. I don't,
Okay.
no, no idea, sir. No idea. I have to think.
See, have we not already proved that F inverse A intersection with F inverse B, this is equal to F inverse of A intersection B? Have we proved this?
Yes, sir. Understood.
But A intersection B is empty, right? So this is F inverse empty. We have also proved that F inverse empty set is empty set, correct?
Yes.
So these are two proofs. Again, this answer is yes. And therefore this is correct. Okay. Now once this is correct, it means A complement can be written as disjoint union of elements of F inverse C. So A complement must be inside F inverse C. So what we have proved? We have proved this result. So let X and Y be non-empty sets. F from X to Y be a map. And let C be a semi-algebra of subsets of Y. Be a semi-algebra. Then it's sort of pullback. So it is not the standard notation. Yeah, I am calling it as pullback. This, if you define it as F inverse E, where E comes from C, this is a semi-algebra of subsets of X. Okay, so we have two. Now, what are the next questions that we should ask? Yes. Any questions that come to your mind?
Is this algebra?
No, is this algebra? It may not be an algebra, right? Because you already know that semi-algebras need not be algebras. That counter example is easily obtained. For example, see what you take. Look at identity map from X to X. How it is defined? ID X is just X. Then ID of C is just C, right? Now, if this is not an algebra, sorry, ID inverse of C is just C. This is not an algebra, then this is also not an algebra. Correct, Sashikant?
Yes, sir.
So, yeah, whether this is an algebra is not really a good question. A better question is whether the pullbacks of algebras are algebras, right? One, if C is an algebra, is F inverse C also an algebra? And what is the next question? Similar question that you can ask. Yes, anyone?
Sir, is a similar statement true for sigma algebras?
Correct. We can ask a similar question for sigma algebras, right? If C in Py is a sigma algebra, is F inverse C in Px also a sigma algebra? Okay. So the proof goes exactly same, and I'll give you the answer. The answer is yes. You can try it. I really wanted to try it. If you face any difficulties, please let me. Okay. Now, before ending, let me just give one more result that I would like to share. So again, f from x to y is a map, and again C is a semi-algebra. Y, this is a semi-algebra. Okay, not really. We don't require semi-algebra, but let us take any collection. This any collection. Then the sigma algebra S generated by F inverse C. This is same as F inverse of sigma algebra generated by C. Okay. So can you prove this? So just give me some ideas to prove it, and then you can fill the gaps by yourself. So these are two sets, right? We have to prove that they are equal. So one has to be a subset of other, the other has to be a subset of the first one. So can we say that the sigma algebra generated by F inverse C is contained in F inverse of the sigma algebra generated by C? Is this true? See, you have these questions and its answer. Okay.
Yes, sir.
Why is it true?
Since sigma algebra generated by C is a sigma algebra, the F inverse is also a sigma algebra. So it must always contain the sigma algebra generated by F inverse of C.
Correct. So this is the smallest sigma algebra. Containing F inverse C, and this is an algebra containing F inverse C. Okay, why is F inverse C here? Since C is in SC, F inverse C is in F inverse of SC. Now, so one way is fine, no problem here at all. The other way is a bit tricky. F inverse SC, we want that it is a subset of S of F inverse. So have we really seen these type of techniques in the lecture? I guess we have. So what do you think? Okay. Let me give you a hint. Let us take this A collection as collect all those sets such that F inverse Y is inside the sigma algebra generated by F inverse C. Okay. Prove that this is a sigma algebra. So I think it is easy to prove. You can try it. If you're not able to do it, next time we will. Prove that this is a sigma algebra. Once this happens, you prove that C is in A. Oh, see, I actually made a mistake. I went to say Y, and then here it is E. So yeah, so this is a collection in PY. So it is a sigma algebra inside Y. Prove that C is in A, which would mean SC will be contained in A because A is a sigma algebra containing C. SC is the smallest sigma algebra containing C. So this containment must hold. And therefore, F inverse SC must be contained in F inverse A. But by definition, F inverse A is contained in S of F inverse C. So this is also true. Okay. Is the idea clear to everyone? Yes, tell me, is it clear or not?
Yes, sir, but we will think on it.
See, the idea should be clear. Okay? In between, of course, you have to write down the rigorous proof of this. But you must have seen this technique, right, in the lectures?
Yes, sir. That restriction and then f of c
Yeah,
intersection e is equal to f of c intersection e.
correct, correct. Yeah, somewhere at that point we stop. Okay, so with this, let us stop. Do you have any questions? Yes, yes. Actually, I will not directly share it with you. The NPTEL team will send you a mail regarding this. Okay, you will get the notes. Whatever I have written here, I'll convert it into a PDF and you will get the notes. Don't worry. Okay, so if there are no more questions, let us stop. Thank you, and we'll meet next Friday.